The internet seems to be working. Do we need a hat? Nah, it's nice in here. All right, team. As we're getting everything dialed in, be thinking about if you have any questions about things you've been working on lately. If you're out in the Zoom world, drop them in the chat and I'll see them in a second when I get everything set up. If you're here, let me know if a question's on your mind. And if not, just have a little patience while I get that little video muted and hidden away from my eyes so it doesn't bother me. And we'll go to our class. And we'll make it nice view, student view. And I'll sign into my PCC email, so that'll let me edit things for our class as necessary. Look at all my technology tasks I must do to get a class to start. It's not that many. Just took 2 minutes, but you don't need to read. Let's not read my email now. Now I can share my screen because it looks good. Turn on the chat. It's empty. Good morning. No need to chat unless you got something to share. No pressure to chat unless something's on your mind. Hide my little video self from me with a different window on the screen. And we're off. We're off. At that, oh, wow. A couple minutes later than I normally like to get going, but sorry about that. That's just a slow move into class today. I insomnia'd last night. I did insomnia, so I'm a little dumber than normal. Yeah, I made the mistake of, what did I do? It was like after 11 and I was like, I just wanted to look up that one thing online. Hours later, I was like, I should be in bed. Why am I watching this particular YouTube video now? I could watch this never. I made mistakes.
YouTube's more interesting at 1 a.m. So.
Yep, that little dopamine hit of that next video I might want to watch feels better when I'm exhausted. As designed. In any case, I don't see any questions coming in the chat. Nothing's happening here in the room. So let's check our plan. I'm pretty sure I know it, but I always like to double check. I'm heading to course materials module here in our D2L Brightspace place. Good old course schedule. We're right on schedule, if I remember correctly. Yeah, last class was our Zoom day only. I was at home. It went great. After like minutes after our class ended, my little kid showed up. He could have showed up a little before class ended, but it was perfect. We had a good class. We got through our discussion of that 4th section of chapter 6, and we're in good shape. So let's talk about our next section. It's about inference for a mean. So if you want to either estimate a mean in a population of interest or make an assumption about what the average value is for something you might care about measuring or counting in a population, and then check how likely a sample mean looks in that setting via hypothesis testing. And we're going to meet another probability distribution. Our book likes to call it the T distribution, and that is its most popular name. It's also called the student distribution for reasons we will discuss as part of the history we meet in our discussion. First section of chapter 7. Let's go. Oh, why am I view only? Switch me over to PCC, please. Yeah, now I can edit things as I like. All right, cool. So I'm going to head back into content, get on down to probably my favorite module, slides. That's where the most stuff that I talk about with y'all lives. Hey, chapter 6. I'm going to leave you open for now, although we made it all the way through chapter 6. Let's just remember the theme of chapter 6 was inference techniques for categorical data. That was the idea, whether it was one proportion being described for one level of one categorical variable, comparing two groups that way, or the more complicated ideas of checking out how likely observations look in light of expectations with goodness of fit, or considering independence or so-called homogeneity in contingency tables. Those second two ones using the more complicated analytical tool, the chi-square distribution. Good times, great oldies. Okay, chapter 7, we're going to shift gears. You can see the first section, one sample means. Second section, it says paired data, but they're pairing up like before and after or similar types of like pairs of data where you're measuring or counting something. So it's going to be numerical pairs of data. Difference of two means, still numerical data. And that last one, comparing means, it's just for more than two groups with a technique known as ANOVA, short for analysis of variance. So the theme here in chapter 7 is inference for numerical data. Let's party. This stuff is fun. I lied. It's not bad. It's as fun as the other stuff. So if you thought the other stuff was fun, you may find this fun. If you thought the other stuff was, interesting, this is just as interesting. If, some days I think it's fun, maybe. All right, kind of boring section name, one sample means. What they're just saying is, if you take one sample from a large population and you're looking at one measurement or count, taking the average, the mean, how can you do inference? That's confidence intervals and hypothesis testing. And the answer happens to be using this new distribution we're going to talk about today, the t-distribution. Oh, let's look back. Let's look back in time. Remember the olden days? Let's even put this in our class notes. It says, let's sketch and label the distribution of sample means as described by the central limit theorem. So if you took statistics 1 here at Portland Community College, you talked about this for at least one class session, probably, maybe, and it comes up in some different contexts, but let me remind you of a couple of important things. Maybe I'll just try to make my drawing right here by making a fake piece of paper, and then I can put it into the notes, but I'm going to use the Zoom tools for my drawing, so. Oh, there's the insomnia. How do you draw when you're tired? There we go. I'm just going to make a little piece of paper at the top of this slide. Oh, see that? Ah, that's nice. And we'll still have all these notes to guide our little drawing. Two important conditions for the varying sample means from different samples drawn from the same population. Samples have to have independent observations. So no single measurement or count has any direct impact on another measurement or count in a data set. And either you've got a population distribution that's fairly unimodal and symmetric, like fairly close to a normal or bell-shaped curve. A little skew's fine, a little funkiness, but as long as it's fairly close to bell-shaped, you can have as small a sample as you like. If the population's distribution shape is either unknown or you're well aware that it's drastically skewed or has multimodality or something, then you need at least 30 for sample size for this theorem to work. The picture just matches the first bullet. The sampling distributions of sample means is nearly normal. So it should be a lovely bell curve. Let me see how my mouse writing is after not getting quite enough sleep. Can I draw a bell? Yeah, I'm with it's a round of applause. That's a pretty good bell. And remember here in this picture, that's an axis, right? And on the axis is varying sample means from sample to sample drawn from the same population, all of the same sample size. So set sample size at n, and you'll have as this, I'll just label my x-axis as x with a bar, or just x bar when I type it. But if you have a handwritten notes, I'd go x with the bar right on top, like in your stats book. That's varying sample means from sample to sample. Oops, I just made a mistake. Can I undo it? Yeah, all right. Now, of course, it's going to be centered at, and I'm going to draw this in red, because if you're doing good sampling, you should get dang close, like you should get really close to the sample, well, if you have good sampling, random samples, you're looking at means. What number should your sample mean be close to, hopefully? Well, it should be 0 standard deviations away from, we're gonna be in the middle. 0 would be the middle of like a standard normal curve. But in this case, if we're thinking about, let's say we're taking the number of credits, the population number of credits that PCC like stats students are taking this quarter, right? So if I took all my students this quarter, just as a convenient sample, and got their average number of credits, if my students this quarter are a fairly representative sample of all the statistics students here, my sample mean should be close to the mean of all the students, right? The population mean. So varying samples means should be more likely close to the population mean than anything else. So I'll write that. It's a Greek letter, mu, but I'll also just type population mean. And I'll put it in red. Just that's my color for population information in my notes, largely because in many, many settings, it's a number we don't know. So there you go, centered at mu. And the standard error is the variation of those means. So it's really the standard deviation in the curve should pick up about 2/3 of the sample means that you'd expect in a random world. And there's its formula, standard deviation. S is population standard deviation divided by square root of the sample size n. And that is the estimate for how sample means should vary from sample to sample, drawn from a large population, according to statisticians' beloved central limit theorem. Yeah, stats 1 reminder. And let me just label the standard error in there as well. Just with the phrase SE for standard error, we've got the formula right there below, right? Standard error SE equals S. I'll call it population standard deviation divided by square root of samples. So for my notes, I like to have that just always emphasizing in red, population stuff. The crucial reason that statisticians love this theory, just to remind everyone, took this a while to sink in for me as a teacher even. It's this connection that the sample size n is like a crucial number here. The bigger your sample gets, the less variation you'll expect in your sample's means. And that's cool. Bigger samples are better for your research. And then there's the bonus crucial idea is that how big your sample is, as long as it's a good random independent sample, has a direct impact on your ability to make estimations about the population, this connection, sample information and population, variation, standard deviation. That's just this crucial thing that statisticians care about. So maybe a little heart there by that formula because it connects the sample size to the, well, important facts about the population in a really interesting analytical way that statisticians absolutely love. So it's the central limit theorem. I'm going to snip this drawing and just dump it in our class notes, just so in case anybody ever likes it or wants to see it, I'll have it snipped for you. Hey, computer, what are you doing? Snipper, there you are. I was going to change one thing about this computer. I just put the snipper right there in the toolbar at the bottom of the screen. I can't because I don't have the power to like change anything. Oh wait, now I'm having trouble because the snip window logo shift and 5. Okay. Oh yeah, I see I see. You got me. Thank you. I'm still having the issue that I'm having though, because my snip window came up under my Zoom garbage. Well, my dream of taking a quick screenshot has died. It's just one step too complicated for me. That bell's going to go into the bin of YouTube. All right, cool. But I'll get my snip window in a smarter place for the next time I want to try it like that. All right. Okay, team, so this normality condition, central limit theorem says sampling distributions should be nearly normal. Should hold true for any sample size as long as the population distribution is nearly normal. Okay, cool. Some very nerdy nerds developed this theory within the last couple of 100 years, and they all convinced each other that it holds analytically. Okay. Now, it is difficult to verify if a population has a nearly normal distribution when you've only got a small sample to consider. That's one truth here. And so there's a note, exercise caution. Let's put a star here. Exercise caution when verifying the normality condition for small samples. It is important to not only examine the data, but also think about where the data came from. Usually if you're measuring things that are comparable, like say you're doing quality control in some production process, and all of the things being manufactured need to be measured, there's going to be variation. Some things will be bigger on the measurement scale, some smaller at random. And that's often going to be expected to be normal. If you're a pediatrician and you're measuring 8-year-old boys, their variation in heights and weights is expected to be normal. There's kind of a common average, and heavier and taller kids are rarer than shorter and smaller and lighter kids. They have different curves, of course, but so there's places where you can just convince yourself that things should be normal because we're measuring. There's also, in examining the data, the smaller your data set gets, the more useful what's called a normal quantile plot becomes. And we'll use those sometimes in some of our examples, especially in chapter 8, when we have some small data sets and we want to check this condition. Or actually, even at the last section of this chapter, I'll show you at least one numerical way to check this with a graph that's better than just looking at a dot plot or a histogram or something. So there's options. There's options, but you can use caution, and you can use some good techniques to check that condition as needed. And research teams are well aware of this and should have the best method. Yeah. There's the question, if you don't know anything else to ask and don't know the tools, would I expect the distribution to be symmetric? And am I confident that outliers are fairly rare? If you can answer yes to both questions, you're probably safe making that population assumption in just a random stats textbook exam. Pretty cool. Okay, the t distribution. This is our new distribution. When we got to the chi-squared distribution a couple sections back, I think I just popped open GeoGebra to get a look at it. Let me show you how the t distribution looks in GeoGebra first thing, just so you can see the picture. I'm heading back to our D2L page to wander through to the links, where I've got my direct link to good old GeoGebra Classic, our probability calculating pal. My window's big enough to see probability right there on the main list. Of course, if your device or your window is smaller, you might not see this list. Always the reminder that those top 3 arrows up there give you the perspectives options or the view options. Both, you can select what you like. I like the view because I can just turn on what I want. I want my little curve, but I don't need graphics or algebra on my screen. Cool. Bye-bye, main menu. Okay, we've worked with the normal distribution this quarter, and we've worked with the chi-squared distribution, which is skewed to the right. Checking out our list here. No t distribution anywhere. Hold on. The t in that t right there, that is the last letter of AKA. Oops. Let's make that a friendly blue. That T is the last letter, student. See that student distribution? There's two reasons that it gets shortened to T distribution. I'll show you the other one as we talk more about it. But see that the last letter of student rather than the first letter, T distribution. So in GeoGebra, if you want to look at or work with this distribution, the T distribution, just select the student option. And look there. It's a unimodal symmetric curve. Okay, cool. Let me actually just, okay, cool. Let me just, wait, let me shift back to the normal distribution, our old friend from chapters 4, 5, and 6, if you've worked in this book all the way through the book at PCC. Just a little different shape. Remember the normal distribution. To work with it, we just have to know the mean and the standard deviation. Those numbers, they measure stuff about this curve, like where it's centered is the mean and what amount of distance you have to go to pick up about a little more than 2/3 of the area in both from the center is a standard deviation. And those two values, you can draw that curve in different shapes and sizes. With our T, or student distribution, this next option, still a bell curve, but look at that. Instead of having the mean and standard deviation under our control, they're still up there as measurements, mu, it's centered at 0, and standard deviation for this curve we're looking at is a little more than 1. But to draw the curve, we need to know a degrees of freedom number. So it's a parameter kind of like it was for the chi-squared distribution. It's going to be related to our sample size and maybe even our sample's other characteristics sometimes. Okay, interesting. Degrees of freedom. Let's go back and learn more. When working with small samples, again, this is normal in all research, population standard deviation is, they're saying almost always unknown. Certainly it's often unknown. And the uncertainty of the standard error estimate is addressed by using a new distribution, the T distribution. New, they only mean new to us today. This is a couple of 100 years old as an analytical tool. But what do they mean here? The uncertainty of the standard error estimate is addressed by what? They cut out like a big history story here that's kind of interesting. I'll try to tell it the shortest way. I'll try to tell the short version by memory. Okay. Oh, perfect time. You came back for an interesting history story that's not on the slides here. So, I've got this student T distribution. It's got this funny phrase here, the uncertainty of the standard error estimate. And they're talking about small samples and their standard deviation for the population. Okay. There was this guy, one of those terrible men of the UK, Great Britain, who helped develop statistical techniques in like the 19th century, named Gossett. Gossett. Hear that T at the end? Gossett. Ah, okay. Hold on. See that Gossett distribution? See the T there? That's the other T. It's the guy who came up with this. His name ends with T. But the story is interesting because it tells us why it's not just named the Gossett distribution. There's a kind of an interesting tale here. Okay, so I gave the example of a manufacturing process as a place where you'll see variation in sample means. Gossett, one of his jobs he wasn't just he didn't work at like a university all the time and wasn't always a stats professor. He worked in industry. One of his jobs was as a data analysis person for quality control for the Guinness Beer Company, the people who make, back then as today, one of the most delightfully delicious stouts a person who does partake of things like beer can enjoy. If you're not a partaker of that stuff, don't worry about it. But if you are, It's delightful, especially on a cold day. In any case, he was well aware of how the central limit theorem works. Analytically, it's supposed to give you, the distribution of sample means varying from sample to sample should be a normal curve. It should look just like in his notes. I bet he was had lovely notes where he could draw bells that looked just like this and label them as needed. He was confident that as he was getting more and more, there's numbers on cans of beer or bottles of beer you buy now that they measure things like alcohol by volume. And then there's other measurements that count like things like, other things about beer. I don't know what those are all called. But it was one of those numbers, one of the numbers that Guinness Beer cares about, that's important for them to get close to in making their beer. They want to maintain one of these measurements. Though back then, the measuring itself was challenging. So the quality control, he would have small samples, like 10 samples to 10, measurements per sample. So like, that's a small sample. And as he was working there for months, he got more and more and more samples. So he started to actually build up, like imagine a dot plot building up. Here's a high sample this day. Here's a low sample that day. Sorry, sample mean this day, a lower sample mean that day. Here's a sample mean in between those two. There's one, and they're stacking up. He's starting to get a histogram to develop the shape of the distribution. And the whole time he's like, cool, it's unimodal, it's symmetric. But then as he went along and he started to get more and more confident that he had enough data that it should match this normal curve, he also was like, okay, I've got tons of samples. This should play out exactly like the theory. But when he looked at the numbers and looked at the actual likelihoods of like very high means and very low means on the scale, they were happening more often than the normal distribution would predict. Like the tails of his bell curve were thicker than they should be according to the central limit theorem. And he's like, huh? That's weird. Huh? And that is the uncertainty. So like there was this wiggle in how big that standard error should be because of these things happening a little bit differently than predicted. Gossett did more work, both empirically with beer measuring, and he like looked into how and why it was happening in the numbers and analyzed it. And he discovered or developed this new distribution, the T distribution. If we look back at the T distribution, it's got, can we see it on our screen? Focus your eyes right out here at like one of these tails, okay? I'll go back to the normal distribution. This is the student T distribution we're looking at, student. There's the normal distribution. See what happened to the tail? It like went down. And when you go back to the student distribution, it pops up just a slight amount. That slight difference was enough to be noticeable in the data sets, and then he developed this curve to account for it. It gets thicker and thicker the smaller the samples get. Bigger samples, the bigger they get, like once you get past sample size, I don't know how big, more than 30 definitely, but even maybe more than that, it'll get closer and closer to a normal curve. And that's when you drive up the degrees of freedom number. Let's put it at 50. See that? It smashes down when I dump up the degrees of freedom. It looks more normal, the higher degrees of freedom go. So he developed this curve that takes small sample sizes into account. The degrees of freedom is directly related to sample size. So when it draws the curve, like a sample of size 5, much noticeably bigger tails. All right, nice job, Gossett. Wow, you did all this cool statistical work. Okay, so as an excited, monstrous eugenicist and statistician, Gossett, of course, wanted to share this new distribution with the community of horrific eugenicist monsters, statisticians. And he wrote his article for the Journal of Statisticians about the process. It detailed his data set, it detailed his analytical discoveries and ideas. And he said, hey, boss, to the Mr. or Ms. Guinness, or the manager at the Guinness factory, I'd like to submit my research based on our data here to this journal. It's going to have a really big impact on how statistics are done all over the world. This could make manufacturing better for everyone. And his bosses said, bang, no way. You work here. That's our data set. You cannot submit your article. We own it. You work for us. That's ours. So just the usual crappy proprietary approach of any company or corporation who doesn't ever want to share anything that could possibly give any competitor any advantage in the market. Jerk move, Guinness Corporation, or sorry, company, though I still support the wondrous, delightful deliciousness of your product. Well, so Gossett didn't like that. He's like any very entitled white guy, he then was like, well, what am I going to do then? And he just took his article, erased his name, and he wrote a student, like a statistics student at a university, a student. And everywhere it said Guinness and beer, he just wrote company or something and wrote product. Like he just anonymized the entire study, erased the context of the beer corporation, and published it under the name a student. And then I don't remember what he called the distribution himself in his paper, but statisticians, his fellow awful monster eugenicists at the time, and maybe there was even a few cool statisticians back then, I hope, but they, in honor of his work, the name ended up being T, both the last letter of student and the last letter of gossip. So that's the long story that gets us the multiple names of the distribution and somehow reminds us that it's kind of cool. I think the story is that the central limit theorem at the time of Gossett's work was this jewel of statistical analysis. And then someone did enough work in day-to-day life, in day-to-day work, looking at actual data sets to say, our theory is great and it's true as a theory, though it doesn't always work. And then even though he was a terrible monster as a human being, he still developed a much better theory that does work, that does take care of these sample size issues in a cool way. So bad job being a horrible monster, but good job, Gossett, developing a very useful tool that people still use today. Clickety-clack. All right. I already mentioned and showed you the distribution's bell shape, and we've already seen its tails are thicker than the normal model's tails. We looked at those as pictures. Thicker tails mean observations are more likely to fall, well, further from the center, and more likely to be beyond 2 standard deviations from the mean. So this affects things like our margins of error are going to get a little bit bigger, and p-values, you're going to need to be have a more extreme sample mean relative to your expectation to get a low p-value. And that's a bigger difference compared to, say, the proportion world or the normal measurement world, the smaller the samples get. And you can even see for that, when we open up GeoGebra, that's when you're at low degrees of freedom, thicker tails. See the standard deviation there is 1 and about 3/10. If we go back to, I think 10 was the initial setting, it falls down. So like the tails are getting smaller, the standard deviation shrinking in a little bit because the tails shrink and there's a little more space in that, the pointy part of the bell, the peak. Just interesting little details. The thick tails resolve the problem that Gossett observed. So he figured that out in the context of his research. With a less reliable estimate for the standard error when the sample size gets smaller. If you're using normal stuff. And that's technical. I told the story. That's a technical rephrasing of how they say it. And they just have 2 pictures on this, a picture on the slide to show us right next to each other, the normal curve and the T. See how the T curves, when it has thicker tails, its peak will have a slightly different shape and be a little lower in comparison to normal and their style of how they make it on their slide. We can look at the difference in GeoGebra as well, because GeoGebra will always draw you a normal curve as this red line here. Let's go for low degrees of freedom, like, I don't know, 3. Nice thick tails there. If I tap this normal curve, it'll just draw a normal curve with the same mean, 0, and that standard deviation of 1 7/10 and a little more. And see there, this way it looks a little different. These tails are so thick that, yeah, you have to have way below the peak of the normal curve in the middle. Sorry, the tails are so thick out beyond there that then it comes under the normal curve and then back above to catch the shape. So depending on the degrees of freedom, the relationship between where the tails are above and below can look noticeably different. Again, as degrees of freedom get bigger, at 10, see the normal curve is now closer. That red curve is closer to the student T curve. At degrees of freedom 25, they're getting pretty dang close to each other. And once you get up to degrees of freedom like 100, the two curves are nearly identical. And at this point, back in the olden days, you might have stuck with the normal distribution because you didn't have a computer where you could quickly use high degrees of freedom for your calculations. Kind of cool. Good times with the old-timey history of the t-distribution. All right, cool. Okay, there's a slide that kind of captures what I just did as a little act on the computer. As the degrees of freedom parameter increases, the t-distribution gets more and more like a normal curve. So you can see that black, the darkest curve here is the normal curve, and the lighter and lighter and lighter and lighter curves have lower and lower and lower and lower degrees of freedom. They graph them in a lovely way, in a nice window that like stretches out the differences, especially for the tails. And you can see they almost have like it's not like at the standard deviation spot, but somewhere out there, I don't know, between 1 and 2 standard deviations in this world, you get this zone where they're going to meet, but they're going to be different both in the center and out in the tails. Kind of cool. Kind of interesting. Nice job, t-distribution. You're interesting. Degrees of freedom. Cool. Okay. You're welcome, Tori. Oh, I already told the story. We're not going to ask the question. What happens to the shape we can see? And I've told you the story already. So sorry to spoil the little question. Spoiler, I spoiled the little question. Okay, so with this tool now, regardless of sample size, if you got a sample mean, small sample, like smaller than say 30, where you get this, the central limit theorem tends to play out. Regardless of sample size, you can use the t-distribution to make confidence intervals for sample means, as small as they are, or heck, as big as they go too. So let's look through here at how this works. Good old reminder. Every single confidence interval has the same basic form. It's always going to be our point estimate. So that's our sample statistic. In this case, the point estimate will be a sample mean. And then it's going to have a margin of error. The margin of error is based both on stuff related to the sample, like sample size and standard deviation, but also, of course, I'll use some green there as well. It's going to be related to how confident we'd like to be in our estimate. That's going to give us a critical value. Okay. Yeah, margin of error calculated as product of critical value based on our confidence level and standard error, which is a number that we calculate based on either our sample data, if we're doing an estimate for a confidence interval, or based on our population assumption, if we're doing a hypothesis test. Or sometimes, well, we'll see some examples. In this world, it's almost always the sample standard deviation, because it's kind of hard to make an assumption about standard deviation. Oops. Is there more? Oh yeah, so since small sample means follow a student t-distribution, not a normal z-distribution, the critical value is called t star, right? T, last letter of student, last letter of Gosset. So there's our critical number T star. And point estimate, that's again our sample mean. And standard error, well, it's going to have a formula a heck of a lot like the formula we saw for standard deviation for varying sample means. Yeah, not just a heck of a lot like it, exactly like it. So there we go. Our little formula is sample mean. There's the standard error. That's the sample standard deviation S divided through by the square root of the sample size N. And we got our critical number. And now we're in the position to go ahead and do confidence intervals for small samples means, or heck, for big samples means, if you want to be more accurate, the student curve and the normal curve, they get closer and closer to one another, but they never quite meet. So it's just a good theory all the time for these means. Hey, and our slides had no example for us to do in them, so I had to grab one from the book. I think that's from the first edition of the book. But let's read it and then we'll get to work on this. Let's see. Let's read this to get settled in. Let me just check here too. Hold on. What do I have here? My memory's bad. Yeah, okay. We'll work through this as an example, like in our notes, but let's settle into it and look at it here too. Age at first marriage. The National Survey of Family Growth, conducted by the Centers for Disease Control, gathers information on family life, marriage, divorce, pregnancy, infertility, contraception, and people's health. One of the variables collected in the survey is age at first marriage. I've got exactly one marriage. I'm trying to remember my age. It was 2010. So I was, all right, I'm not, am I an outlier? 38? 38. I was old. There you go. I'll tell you, it doesn't help to wait to find one that's going to work. Sorry, bad marriage. That's me. I was one of the people. One of the variables was age at first marriage, a depressing statistic for many people, for about half the people. The histogram below shows the distribution of these ages for 5,000 plus randomly sampled women in the late aughties, basically. The average age at first marriage among them was 23 and 44 hundredths, with a standard deviation of 4 and 72 hundredths years. Estimate the average age at first marriage of women with a 95% confidence interval and interpret it in context, discussing any assumptions. Well, I guess I didn't pick the best example because it says small sample up here, right? Oops, sorry. It says small sample at the top of the slide, but that's a pretty big sample, right? 5,000 plus. But the cool thing is it doesn't really actually matter how small the sample is. It can be any size and you can still use this theory. So we'll just use this big sample for our example. Well, it's almost 9:50. Should we just take a break and then walk through this process, get the 10-minute stretch break, and then we'll come back? I'll set this up so I can look at this in our class notes on the break. That'll save us some boring tech time in our discussion. So see you back here in 10 minutes. And that'll be officially 59 minutes past the hour, 9:59. There we go. And I appreciate that. Passive aggression's good sometimes. I'm like, whoa, I didn't know that was even here. I can clean the whiteboard. Cool. There's no training. There's no training. They just leave us to mess up and then get passive aggressively, annoyed with each other. Okay, let's do this one in the reverse order from our usual calculation examples, just because as we're getting into things, remember, we've always got two ways to go with calculations. We can use all the formulas and carefully work through things step by step to get the result correct. Even if we do that, we should double check what we've done using technology, right? So this time, let's go technology first, and then we'll peek at the formulas and double check that technology worked and we know how the formulas work. Let's go backwards from before. So let's work through this. Let's work through this. Let's work this out using, let's go technology. I'm going to use our buddy GeoGebra, and unsurprisingly, it's going to be in our probability calculator. So if we want to just go straight to making a confidence interval for a sample mean, there are two options in the statistics world over here. So the statistics side of GeoGebra is my destination. Very first option does have something for us there. It says Z-test of a mean. Z, normal. Now, look what we need to know. Oh, sorry, wait. We're not doing a hypothesis test, Ralph. Slow down, silly. Estimates, right? Estimates are confidence intervals. In the world of GeoGebra, we have two options. The Z estimate of a mean, that's the first one. This one works only if you know sigma. Sigma is the symbol for the population standard deviation. It's rare. In fact, you will never know the population standard deviation in any examples or homework problems we're going to see this quarter. So since we're never going to know this number, sigma, let's never use a Z estimate for a mean, okay? Sometimes the textbook might do that because in an anachronistic world, when samples are very large, you may as well assume you know, but those are long, boring arguments in modern times because now we have a T estimate of a mean. The next one on the list uses the student T distribution, and it does so if you want to make an estimate, and welcome, and well, how confident you'd like to be in your estimate, and you have sample information, and that's what we've got in this problem. We know the sample mean, we know the sample standard deviation, and we have the sample size. Sample size is huge. This works just as well for huge samples as for small samples. But that correction to tails is not important, but still, we don't know the population standard deviation, so let's use the correct tool for the job rather than the one that they would use in old-fashioned times because they didn't have technology that we have. So cool. Looky there. All I need is the sample mean, sample standard deviation, and sample size, and I can get this calculation done. Let me just note them here. Sample mean is, we just need confidence level, X bar, S, so X bar, sorry, sample mean, X with a bar, sample standard deviation S, and sample size N. And they're all right there above. They're asking us to make a 95% confidence interval. So my confidence level is going to be 95 hundredths. That's the usual setting over there in the world of GeoGebra. Let me make this note a little bit bigger so we can see it better. Ages at first marriage. The average age in the sample was 23 and 44 hundredths. That's my sample mean. So X bar is 23 and 44 hundredths. Sample standard deviation right there. S is 4 and 72 hundredths. Sample is not small, but it's 5,534 randomly selected women in that time span. Right? 5534. And 5534. There's the numbers. I'm just gonna, like, I'm gonna have to type them twice, but that's how I did my notes. I like to get things sorted out when I'm working through homework. Whenever there's a big paragraph, I want to get stuff sorted out into my notes with the symbols, because that way, when I do head to technology, my notes largely match the technology. So the number I remember is 5534, because that's the sample size that I just typed. I think the standard deviation was something like 4.7, oops, 4.72, 4 and 72 hundredths, is that right? Nice one, brain. And 23 and 44 hundredths years of age for the sample mean. 23 and 44 hundredths years of age. And looky there, just like back in the days of confidence intervals for a proportion or confidence interval for a difference in proportions, the moment we've entered all that information into our buddy GeoGebra, we've got down here the lower limit of our estimate, the upper limit of our estimate. Well, there's the sample mean again showing up right there at the center of the confidence interval, and the the margin of error right there, 12 hundredths of a year or a tenth of a year. Kind of a weird number, tenths and hundredths of years. If we were cool, we might translate it into months if we wanted to share the number, right? But I'm not that cool. I'm just going to call it 12 tenths of a year. So here, let me finish brewing this tea. So for my notes, let me just get this cleaned up. I will get a screenshot of this now that I can do so easily and quickly. I'm here in GeoGebra Classic. I'll get all the good stuff in my screenshot. Web page all the way down to the result. Bam, make it less big. And in my notes, because this is still new for us, I'm going to say confidence interval or 95% confidence interval is from 23. Do you care about the hundredths of a year at all? Hundredths of a year? It's like a couple of days. I don't care. Let's go 23 and 3/10 rounding it off. Upper limit 23 and 6/10 rounded off to the nearest tenth of a year. We've got, and margin of error is, I'm going to call it, well, I'm going to hold on to the hundredths there because it's like such a small number, 1/10. I want to just know it's a little more than a tenth. Oh, now that I did that, I do care about the hundreds again. Ah, curse me. All right, 32 and 56, because that'll make it look better in my notes, I think, notes wise. And I started with the hundreds. Remember, I had that 23 and 44 hundredths. That was my, I'm going to stick with the hundreds in my work. Cool. So that we can see quickly is the calculation completely relaxing here in this world of technology. Yay, technology. What fun. Oh, we're not done yet though, right? Fatima just walked in here in real life. Were you here when we were talking? Were you listening when we were talking about the context? So you know we're talking about people's age at first marriage and all that. Okay, if someone else either walked in here now or just joined the Zoom room, you know, because something had come up this morning and they're like, oh, I'm late, but I'm still going to go to class. And they made it here right this second. They would see that calculation, 95% CI 2332236 ME 012, all these decimals and parentheses everywhere, equality symbols, and they'd be like, what the heck? What does that mean? Right? So the most important part of this conclusion of this process is getting to our conclusion. Like, what is that? What are we estimating again? And what's our range? And how sure are we? How do we just put that in a lovely, meaningful conclusion? And I'm not even going to bother to grab my Zoom annotation heart stamper. I'm going to type out hearts the old-fashioned way. The conclusion's the most important thing. We love it. We love it. Stars and hearts, old-fashioned stars, old-fashioned hearts. How does that look? Artistic? I think so. I think it's So remember the conclusions for confidence intervals. It's been a few weeks because we did all those chi-square tests and goodness and fit tests. We want to communicate clearly what we're estimating. That's our parameter. The range, and we can state that either as from the low estimate to the high estimate, or we can give our sample mean with its margin of error. Either way, just so the range is clear to people reading our conclusion, and mention somewhere how confident we are in our estimate. Those three. Want to practice writing one before I write one? Yeah, practice. Write down in your notes. If you're a typist, type one up. If you're a writer, write one down. Oh my goodness, I thought, did I just see someone just arrive? If you just arrived, it's like perfect. You're the perfect arrival time because I just said, if someone walked in here just now, they would have no clue what the numbers on the screen mean. And we are right now writing conclusions for that T estimate of a mean with no context. So I thought I just saw, I think I saw someone just come in. So enjoy. When someone shares one, either just shares one vocally in the room or chats one to me, we'll have a student version. And of course, I'll share my style too. So we'll have two styles to look at because there's many, many ways to write a good confidence interval conclusion. And if my eyes didn't deceive me, if you just joined us, we're looking at this slide so you can get a peek at the context yourself. This confidence interval for a small sample mean example. That is the 7th slide here in the 7-1 slideshow. That's what we're working on here in our course notes, or class notes, pardon me, class notes. No problem, direct messenger. Welcome, welcome. You never need to apologize for being late, though I appreciate it in the spirit with which it's offered. Gladly accept your apology, though it's not necessary. So yeah, just chill. You will enjoy some good conclusions written by one from a classmate and one from old Ralphie. After some seconds pass. We've got a suggestion in the chat. So if you're still writing and thinking, let's give people another, 30 seconds, 2 tea sips. Good old confidence interval conclusions. Gotta love them. Cool. Let's check. We got a suggestion from Quincy out in the Zoom world. Let me just copy it into our notes so we can all see it together. And in the future. So meaningful conclusion. Student version. Unless you want name credit, Quincy, I could say Quincy version. But I know most people are good just being, our roles. I want to encourage more people to share. If anyone were embarrassed by being named, I wouldn't want to discourage them. See what I mean? See what I mean? Yeah, we are 95% confident. That checks our confidence level, communicated clearly, that the average age of women when they are first married, check, that's our parameter, is between 23 and 32 hundredths and 23 and 56 hundredths years old. A few months, you mean like the span, the span there is a few months, right? Yeah, it's good. Oh, great. And there's another option here. Bonus student version. Let's look at this one too. Great. Ryan's shared one as well. Student version. I'll call it student version Q. Bam. Student version R. Instead of A and B, I went Q and R. Get it? They're in the same order and they make sense with the. Here's this one. I'm 95% confident that the true mean, totally, that's mean for population mean, and average and mean interchangeable in language, so use either one anytime you like. I am 95% confident that the true mean of when women get married is at 23 to 32 to 23 and 56 hundredths years old. Also good. Love it. These are great. I'm very pleased. Looking good. Great work. Oh, I just might add one. The only thing missing from one of them is that word first, right? So it's their first marriage. People can get divorced and get married again. It happens. Some people get divorced and they will never marry again. And they're also not women. You learn stuff about yourself over time. Oh, sad things. Oh, thanks for all the help, therapists. Um, instructor version as well, just so we can get past this painful sorrow. I usually start textbooks and train us to start with the confidence level. I usually start with my favorite phrase, we estimate, right? Because that I'm 95% confident that, or we are 95% confident that phrase makes sense, I think, to statisticians, because they all know we're estimating, because that's their job as statisticians. I, as a person who talks to a lot of people who are not statisticians, not just students, of course, but my colleagues and people I know in daily life, I'd say we estimate that women, sorry, US women are between 23, I am going to round it off to tenths, 23 and 3/10 years and 23 and 6/10 years old when they first marry. Wait, sorry. I'll just say at first marriage. I feel a little weird about it is kind of hard to describe this one well. You did better than me, I think. You saying when women first get married, that's the age. Yeah, you're right. The age of US women. I'm having trouble. My brain is melting. We estimate between 23 and 3/10 years and 23 and 6/10 years is the range. I'm having trouble. My literary trouble was I felt like I was mistakenly saying that all the women in the US get married sometime. My writing was bad, so I was having a lot of trouble phrasing my description how I like. I didn't want to just copy and I was trying to come up with one. And I hope that shows that when you're tired and because you did a little insomnia thing, just getting the phrasing of these things clear and kind of concise can be a little bit of a challenge. So you don't have to write these perfectly, but you want to just make sure that you're satisfied that you're writing something clear. Like you saw with Quincy and Ryan's examples, there's lots of ways to do this. I thought theirs were clear. Uh, maybe I should have been working on mine while I gave you all that time, so I wouldn't be, but I think it's good to role model that we backspace and make mistakes and stuff like that too. I just have to write with 95% confidence, the estimate, our range, that range has the genuine mean. Like, and I'm going full, I'm a stats teacher who knows that, 85% of people on the street have no clue what the phrase I'm 95% confident that actually means to statisticians. And I keep writing that out in life as plain a language as I can, just to practice using plain language and avoiding jargon as much as I can. You all, of course, are welcome to use statistics jargon as much as you like in your work because it's being role modeled for you and you're learning it. And of course, I understand it as your stats teacher. So it's a trick as you learn jargon, whether it's here or in psychology classes or in like business worlds, in the medical fields. It's a real challenge to both learn and understand terminology in your field while still being able to speak plainly and avoid jargon with regular, or sorry, just anyone outside your field, whether they're, you know, 8 years old or 80 years old or anywhere in between, and whether they share your background or not. Challenges. All right, team. That's that. That's our big calculation for a confidence interval for a sample mean.
The average age is now 28.6 for women in their first marriage.
Wow, so in the last update number, it's bumped up by about 5 years, give or take, over the course of 15 years of history. Wild. That says a lot about, well, a lot of trends and reasons and life things. That's a reminder to me that, well, I don't know if my little son is straight or queer, or I don't know where he's gonna land when he grows up. You know, he's definitely, he gets giggles out of every kind of crush he sees happen all the time. And well, I won't tell details about what he does with his little friends, but you know, he's a curious little boy, and he's also a kind-hearted, caring little kid. I just don't want to let him wander into like whatever ugly expectations of masculinity our culture is pumping at him via social media, because then he might be someone that people would want to avoid marrying who are straight women. I'm guessing that I'm just throwing it out there, maybe a lurking variable in that bumping up age, along with economic straits and challenges to people to settle down. Could be that we're having a weird, more fired up, sucky version of so-called gender wars, or what I just call misogyny and patriarchy. They're back in force. We're dealing with them daily with executive orders from the executive branch of our federal government are pushing people in all sorts of ways, in horrible ways around. So good luck, young people, organizing for a safer, cooler future where you can make a family when you want and how you like. Does that make sense? Good observation, Tori. Sorry, I go off a little bit sometimes. Yeah, and I think that's a great observation because, you know, I mean, I was there in 2006 and 2010, but that's when I was in my 30s. So like I had seen my own friends marry mostly in like the second part of my 20s. But I think in the Northwest, or this community where we're all living, I think the age is higher than nationally. Like I think in places like Idaho, where I grew up, the Midwest, places that are just different places from here culturally, there's stronger social pressure to marry sooner on, well, women and men both, right? And plenty of social pressure on people who are neither women nor men, or happen to not be straight and or not be interested in long-term monogamous relationships. There's pressure on them. Well, like we just discussed, ugly pressure for them to not live and be their true selves, live as and be their true selves. So that's what we can fight against. My little fist is my little punch fist for the faces of the men who try to control people's lives that way. I wish I had martial arts skills. I'm a little too slow and old. I just encourage other people to take martial arts who are young and strong and organized so that they're safe when they defend their communities. Safety, along with strength. Good combo. Okay, team. Yeah.
So, are you gonna let us use GeoGebra to help us get answers, or? Okay.
Yeah. If you didn't hear the question in the room, you always have access to all the technology and tools we're using here. Your notes to help guide your work. Yeah, GeoGebra is always here in the room on all of our system. Out there in the Zoom world, of course, you're using your devices. I would never take away a tool I'm helping you learn to use wisely. I think that would be what I call a jerk move. Yeah, Fatima. Say that just one step louder. Bonus good question. And these are great questions about exams and stuff because we're here in week 4. This is perfect timing. Exams are just like regular class meetings. So if you would like to be here in the room, it's warm. I'm right here for questions you ask. I can come look over your shoulder at what you're working on and help you out with any questions you have. That's the best thing about exams for me, just helping people learn more. If you're at home in the Zoom world, normally that's also good on exam day. Just when you have a question during your exam, on exam day, I'll put us in focus mode, which just means that like I'm the only one who can see anybody's chats. And I'll turn off the screen in here so nobody gets distracted by any screens. And then anybody who has a Zoom question, if we want to look at what you're working on, we'll pop into a breakout room in the Zoom world to be able to have a one-on-one talk, and you can share a screen, or I can share a screen to make that discussion as straightforward and quick as we can to eliminate any confusion about what I'm asking or to help someone like, you know, Mr. Yutz, I'm trying to set up this goodness of fit test and it does, can you double check my result and help me out? Those are all good questions because I want people to succeed. And I'm here sort of as a pal and a coach during exams rather than as a, cop to surveil. Make sense? Yeah, great question. So yeah, here in the room, home at Zoom. Either way, my job is to help you just work on 10 or 11 questions. I think maybe 11 on our midterm and 10 on our final, if I remember correctly. And just, do your best work and ask questions when you have them, because I think of it more of as the dream is it's a learning experience more than it's a way for me to sort you out. So, I really hate those eugenicist guys who sort people out. They're dicks. And by hate, I mean, I want to go back in time, or actually, wait, I want to go to the offices of X and punch the eugenicist in charge, right? In any case, do you want to see the formula version where these numbers come from? Or do you want to just peek at hypothesis testing with technology? And then what do you feel like? Want to go hypothesis testing or do some formula viewing? Because I could go either way. Or do you want to just see what's on the next slide? I think let's pick. I'm like a hypothesis testing person. We got about 20 minutes left. Let's peek at the hypothesis testing world here, because there's just a few differences from the confidence interval work. Just like back in the past with proportions, things are a little different. And if we want to get into specific things like critical numbers, calculating them, and by hand calculations, we'll have homework problems where those will be good questions to talk about too. Oh, great. Is the midterm next week? Oh, another great midterm question. Yes, Ryan, it is. Let me show you on the schedule. It is scheduled for a week from today, So Tuesday we have a day to just talk about more examples and catch up and do some things. I've got some more things that I can dump into the class notes that are pretty good to dump in like after we've done a bunch of sections. I've got some sorting out things, like a table I can share with us, and I'll walk us through that to share that with you that day. And yeah, and then any questions you've got about the homework. This is the weekend, really, like this weekend, to get as caught up on homework as possible, and ideally just bringing in lots of questions. Anything confusing is perfect because our midterm will cover topics up through today's discussion. So chapters 5, 6, and 6, along with that first section of 7.1 are all fair game for the midterm. And let's just peek at the next slide. Hypothesis testing. So yeah, we're switching gears. Let's go to the next slide. It's one of those slides where things reveal slowly and the little formula in the middle will make sense in a second. Of course, hypotheses are going to be about the population, and here it's when you make an assumption about a population's mean value for something researchers care about measuring or counting for a numerical variable. Same assumptions and conditions as a confidence interval for a sample mean. Those were the conditions for the central limit theorem. Independent data set, and if the sample's very small, fewer than 30, you should have some confidence that you've got a nearly normal population distribution. So measurements usually look like that, and you can often convince yourself of that in counts, where there's not a strict minimum or maximum out there. And the last one, but if the sample size is bigger than 30, it's always going to be plenty big regardless of the population distribution. So kind of a complicated sample size consideration and the straightforward checking if things are independent. Random sampling guarantees that. Calculation of the p-value compares the test statistic to the t-distribution. Hey, and there's the degrees of freedom note. I guess I skipped that in the confidence intervals discussion, but looking back at our GeoGebra calculation for confidence intervals, notice the degrees of freedom for this huge sample, 5534 is the sample size. Degrees of freedom is 5533. It's just one less. So when we're working with one mean, the degrees of freedom to properly draw this student curve is just one less than your sample size. Straightforward, easy calculation. Of course, GeoGebra will always take care of it when you're using technology. Though if you're working by hand, the test statistic, T, it's going to have, they put a subscript, so you might put your degrees of freedom as a subscript on there to remind yourself what you're doing in your notes. Point estimate will be your sample mean. Null value, your assumed population mean. Standard error. Notice they're not saying we're going to make an assumption about the standard deviation, so you do use the sample standard deviation to calculate that just like before. Sample standard deviation divide by root of sample size. Low p-value as usual, evidence against the assumed value of the population mean. Depending on the direction of your alternative hypothesis, it might say some more detail. And of course, a high p-value provides no evidence against our assumption. Annoyingly, it doesn't make us more confident in it analytically, just no evidence against it. Depends on the setting, how satisfying or dissatisfying that feels. Wait, do I even have an example? This is the worst slides. There's not even an example here. Is there? Hold on. Ralph, you gotta someday fix this slideshow. This is the worst. There isn't even an example on the slides. Should we just go find one? Go grab one from the world of the universe? Let's go to the textbook and find a not assigned problem that we can just work through. Because it doesn't make sense to not even work through an example here. Let's go look into the section. Yesterday, I was scheduled to have my faculty assessment with my supervisor, my dean, and I had to write up a big self-assessment about my work. It said I should spend more time developing curriculum, like having a good slideshow. Look at me, here I am, the next day, not living up to my dreams. In any case, I'm going to go into links and grab our book. Second edition. I'm going to go, I don't think I assigned, let's just look. I'll check our assignment too. I don't think we've assigned any even numbered problems from this section, so we can grab something. Let me just double check that. Yeah, so in the ebook, we've got, oh, sorry, that's 6-1. I went to the wrong section like a tired person. 7-1. Look at that, 1-3-5-7. Plenty of stuff to choose from, all the even ones. Let's quickly use my eyeballs to grab a good problem for us. Here's one about auto exhaust and lead exposure. Want to try it? I think it's a good one. Researchers interested in lead exposure due to car exhaust sampled the blood of 52 people, police officers, subjected to constant inhalation of automobile exhaust fumes while working traffic enforcement in a primarily urban environment. Blood samples of these officers had an average lead concentration of 124 and 3200ths. Does anyone who knows metric well know what mu-g is pronounced? Is that milligrams, nanograms, tiny grams? Mu-grams, I'm going to say, because I'm not scientific enough to know that how to say it out loud. Micro. Let's go micro. That sounds better than all my suggestions. Micrograms. And micro has a mu sound at the beginning, like an M. Yeah, we could look it up, but let's not. I'm not going to Google it right now. Okay, we got a micro. Okay, 2 votes for micro. I'm fully in. Standard deviation is 37 and 74 micrograms per liter. A previous study of people in a nearby suburb with no history of at least elevated exposure found an average blood level concentration of 35 milligrams per liter. And it's just the 3-part question asks us to do the things we do for hypothesis testing. First, write down the hypotheses that would be appropriate for testing if the police officers appear to have been exposed to a different concentration of lead. You want to go different or just higher? Because we have a huge number there. Different seems like a boring alternative. I'd go higher. So I'm going to edit that when we grab this to work on it. And let's even edit it before we move it. Different. That's idiotic. Let's go higher, greater, right? Oops. Okay. Explicitly state and check the conditions necessary for inference on the data. Mellow, that's an important part of the task. And last, regardless of our answers in part B, so even if we don't think we quite meet the conditions for inference, still test the hypotheses, which means go ahead and do the work to generate the p-value. And we have plenty of time to get this done using technology, as long as I don't talk slow. But if I talk too fast, slow me down. So let me get a snip of this. We'll work on it right in our class notes. Snip, snip, auto exhaust, and lead exposure. Okay, here we go. Back to the notes. Hypothesis test for a sample example. That'll be the name of our little section here. Oops, not heading 1, Ralph. Heading 2. Great. Paste in the work, the problem. And we can just break down a few things here. We can see the sample mean is right there in the description as 124.32 micrograms per liter. So I just get that into my notes. Mu-g, mug per liter. It's bad when I type it like that, but that's the best I can do. Standard deviation for the sample is S for that symbol, 37 and 7400ths micrograms per liter. I'm going to go for a capital L just because it looks better for my notes. And sample size, there were 52 police officers. Pardon me. And something in my nose, I think. I might have a little sinus thing going on. That's all that is. And insomnia. Just insomnia is what that is. Oh. And okay, cool. So for hypotheses here, now notice I don't in my notes the measurement from out there in the suburb, that's just like a different group of people these individuals, hopefully they're comparable in their general lives to the police officers in the sample in some way, like they're from the same population of human beings. Like imagine these were police officers working for I'll just pick a smaller community than Portland, like I don't know, the Boise, Idaho Police Department. Those police officers pretty much live in Boise or in the Boise suburbs, like Meridian and Nampa, which is also where the people who would probably get sampled in that study of the suburb, like Meridian or Nampa, the police would be living in the same community as the people. See what I mean? So that the other research on those suburban folks, think of that as a population mean that we could assume, right? So we can use the suburban study to make an assumption about the population mean. And its Greek letter is mu, so I'll just type it again there, mu. So if someone doesn't have elevated exposure to lead, they should have something like a 35 micrograms per liter lead level, right? Cops live out there in the suburbs. That's also true in Portland. Most of our police officers live in other towns. So in any case, you know. So let's go here. Step A, part A, hypotheses, right? A classic first step of a hypothesis test. Oh, time is running short. I'm not going to ask you to think these through and give me a suggestion. I'm going for it. Null and alternative. Tried to make it really clear what I'm going to go for here in the notes. I even said, I tried to convince you that since the cops are going to live in that suburban neighborhood, it's fair to assume without elevated blood levels, they should be around 35 of these units. So that's going to be my null hypothesis. It's got that lovely equality symbol even in my notes. We always have to pick a value in our null hypothesis to center our analysis. Alternatively, they said different in their assumption, but I thought with this ridiculously way higher measurement in the sample, I wouldn't bother with that if I was doing this research. I'd say, well, let's just consider that mean being way more than 35 and how likely it is for it to be that much higher if we're not expecting elevated blood lead levels. You know what high lead levels does to people, their brains? It inhibits their neural system, and sometimes for children, they'll be more violent, bigger bullies. It raises crime rates, bullying. So it'd be bad if police had elevated blood levels because they have a license to bully people from the state. I mean, to serve and protect people. Yeah, and we can say, so for our null, that's the symbols. I like the words as well. Police officers don't have elevated lead levels, right? That's my sentence, to just have it in plain language. And alternatively, police officers do have elevated lead levels. Kind of depressing considering that people actually are using unleaded gasoline in most cars nowadays. Sucks. Bad job, humanity. The conditions for inference here are relaxing. Again, there's just two. The first one is independent data. The second one is sample size / shape good. So independent data, are these random police officers? Doesn't say, right? So it doesn't mention if they're random or if it's like all of the officers in that community who are doing traffic duty. No indication of random sampling. We just have to assume that each individual officer's individual lead absorption is not impacting the other individual. That's a safe assumption, right? So we have to assume random lead levels among the officers. I think it's fairly safe just because people respond to different stimuli differently in random ways, right? Sample size and shape, good. Our sample size is 52 police officers. That is bigger than 30. So the sample is big. We don't have to worry about what the population distribution would look like. So sample is more than big enough not to worry about population distribution shape. Again, if it was less than 30, we'd want to convince ourselves that there should be a normal distribution here among the population of lead levels in people's blood. And I would probably feel safe with that generally, because most people in a community are going to get similar exposure, even with the people with elevated exposure skewing it somewhat to the higher numbers. I would still assume there'd be quite a peak, because that's going to be a minority of the people you'd hope. In any case, both safe assumptions, both conditions are met, in my opinion, and we're in great shape. And then for calculations, oh, perfect, 3 minutes left. We're going to go back, we're going to use technology again. Let's party with some GeoGebra. We're in the world of inference about a sample mean. We do not have the population standard deviation, so we're just going to stick with a t-test for a t-test of a mean is our GeoGebra name. So that's our routine. I'm going to head right to GeoGebra, statistics side of the calculator. T-test of a mean is the second option there. I'm going to get my null there. It was 35 was the suburban lead level from the study that is a reasonable assumption, greater than, because in the data set we saw a much larger value. I remember there are 52 police officers in the data set. I do not remember the mean number is that one, 124 and 3200s. Tired enough to just cut and paste it. So I hope I typed it right the first time. Standard deviation 37 and 7400s. Again, tired enough to just cut and paste it, hoping I didn't make a mistake along the path. No, probably not a surprise when you look down at the critical number is a big number. It's 17. It's above 17 is the critical number. That tells us in the degrees of freedom 51 curve. So degrees of freedom 51. There's the shape that for the greater than test, that tells us that we're out there beyond, wait, what was it? 170667. There's our test stat, 170667. I didn't have to probably type that to convince you there's no area out there beyond 17 in that tail. Any of these student curves still have that bell shape, and they're all going to get close to the axis around 4 on that T distribution scale. So no shock that the probability of being that big or that far or further from the center here is rounding off to 0. Super low p-value. Snip that from my notes. Come here, little buddy, you sweet little note. You little cutie note. Oh, you good little note. There we go. Ridiculously low p-value. And so then we're at that point where we, at 1050, we can make our conclusion, and it's just going to be instructor version. I just role modeling every time I've got a p-value with a very low p-value. Null hypothesis gets rejected. Yeah, we reject the null. And just like always, I make sure to include some context. We have evidence that Police officers and who do traffic stuff have elevated lead levels. Yeah, or let's call it significant, right? Statistically significant. So, you know, those officers are going to need access to excellent healthcare for their entire lives, just like everyone deserves and requires. But there's a human cost to to their work for themselves, along with for the people with whom they sometimes interact so violently. All right, so now that your goal for the weekend is homework, 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 homework. Get working through all of the assignments up through 7-1, wherever you're at, however far you are in homework, refocus on getting as caught up as possible. The 7-1 assignment isn't due till Wednesday, of course, sorry, Thursday, a week from today, because that's the rhythm. Though if you've got it done as much as you can, or at least to the point where it's, I want to ask these couple of questions, then you're in great shape for Tuesday's review discussion. It'll give us some stuff to chew on together. Yeah, Fatima. The quiz. Today's quiz. Great. I think I've been a bad quiz leader. So great question. Quizzes. You can always do these anytime. But yeah, notice I blew off all the goodness of fit ones. We'll do those. We'll work on them together on Tuesday as little quick review questions because they're perfect reviews for those topics. So just look in there and see what those are. Let's quickly do our T-distribution conditions quiz as a ticket out the door for all of us. Sorry, we're about 3 minutes late. You can run out the door and take care of this later if you like, or you can look at it with me. It's our T-distribution conditions quiz. Boring details. Start the quiz. To use the T-distribution for inference about a population mean, like we did today with both our examples, we need to have 1, independent observations, and 2, expect 10 or more so-called successes and so-called failures. That's option A. Option B, 5 or more expected counts for every category. Or option C, either a sample of size n greater than or equal to 30, or we can safely assume the sample was drawn from a population with a fairly unimodal symmetric distribution. Ding, ding, yeah, from the back row, the C has been heard. Be sure to get that point. The first 2 options were the other ones from the other settings we had. 10 or more successes and failures, that's when you're looking at one proportion or comparing proportions in 2 comparable groups. You got to look at both groups. 5 or more expected counts, that's in the world of goodness of fit and also independence and homogeneity chi-squared testing. But we're here in the world of sample means. So go ahead and make sure to select that last option on the list, submit your quiz and get that point. And then, yeah, we'll definitely catch up on the skipped quizzes together as class discussions because they're perfect review discussions. Awesome. Great work today. Yeah. All right. Farewell. Yeah, let me just mute.